Hello and welcome to next session of machine learning course. Today I'm going to discuss about artificial neural networks, ANN. Neural networks are based on a collection of connected units, neurons, which just like the synapse in a brain can transmit a signal to other neurons so that acting like interconnected brain cell. They can learn and make decisions in a more human-like manner. So if you look at this picture 1, the structure of ANN. ANN are also named as a artificial neural system or parallel distributed processing system or connection system. This picture shows that we have the input neurons, we have the hidden layer, and we have the output layer in neural network that we want to discuss about it. Here you just see the two nodes. It look like the gray color, which we call biased neurons. So in terms of biologically terms, every neuron is connected with other neuron through a connection link. Each connection link is associated with a weight that has information about the input signal. This is the most useful information for neurons to solve a particular problem because the weights actually exceed or inhibit the signal that is being communicated. Each neuron has an internal state which is called activation. See here, activation signal, output signal, which are produced after combining the input signal and activation rule, may be sent to other unit. This is the whole description of ANN. If you look at to this picture, biological neurons, we have a nerve cell or neuron. Is a special biological cell that processes information. According to an estimation, there are a huge number of neurons with numerous interconnection, approximately 10 power 15. As shown in this picture or diagram, a typical neuron consists of the following 4 parts, with the help of which we can explain its working. So some other part of this neuron we call dendrites, soma, axon, and synapse. What is dendrites? They are tree-like branches. Here you see dendrites, tree-like branches, responsible for receiving the information from other neurons it is connected to. In other sense, we can say that they are like the ears of neurons. Another section we call soma. It is the cell body of the neuron and is responsible for processing of information they have received from dendrites. Axon. It is just like a cable through which neurons send the information. This is the axon. Synapse. It is the connection between the axon and other neuron dendrites. So now it's time to describe the difference or similarity between ANN and BNN, biological neuron. What is artificial neural network, and what are biological neural networks? Let us take a look at the similarities based on the terminology between these two. For example, in terms of BNN, biologically neural network, we have soma, but in ANN we call it node. Be careful. Then reads, in terms of ANN we call input, and synapse the weights or interconnection, and axon is our output. That is why I want you to take care of these four feature, we call our feature or phrases: node, input, weights, and output. Now it's time to double check the model of ANN. For the above general model of artificial neural network, the net input can be calculated as follow, or the general model of ANN followed by its processing. Here we have input, we have weight, we have activation function, and we have output X, activation function, and output Y. So let's have a look to this output variable. The output can be calculated by applying the activation function over the net input. For example, the output y in equal to x1 multiplication by w1. This is the weights of input 1, from input 1 to this one, and plus x2 w2, x3 w3, xm wm. Then in total we can sum up everything. Means that y in, which is here, is equal to sigma or sum of xi wi, I from, for example, 1 to m. This is the function that we catch. The function is look like output equal to function net input calculated. Here, function net input calculated. So this is the simple way that we want to calculate y. How? By calculation of x1 w1 plus x2 w2 plus x3 w3 plus xm wm. Sum of them we call y in. Then y in will be our output. Let's have a look to an example, the simple example. Suppose we have a data set of n rows, 3 features and 1 target variable. Target variable is output, 3 feature is input, 3 inputs, and n row the number of records from the data set. The simplest form of ANN is the perceptron. This is the simple ANN we call perceptron. A model with one layer only one layer. Very similar to a linear regression model. Asking what happens inside a perceptron is equivalent to asking what happens inside a single node of multi-layer neural networks. Let's break it out. So we already have this one. Okay, this is the original data set, include x1, x2, x3, and each input variable have the value number. Okay, this one is a step 1. From this row we have the output y. Okay, target, input, target. So if you see this figure, let's say we have a database of n rows, I told you, and all of them are binary, for example, between 0 and 1. So we already go to figure 2. Just like in every other machine learning use case, we are going to train a model to predict the target. Okay, train the model, this one, predict the target using the feature row by row. Let's start with the first row. If you look at our architecture, neural network architecture, x1, x2, x3, it should be like this matrix. So that is why when you have x1, x2, x3, is it your input? For example, input 1. Okay, input 1, input 2, and input 3. So now we have 0.5, 0.1, and 0. So what does training a model? This one, after you justify the input variable, now in figure 3 we have to say what does a training a model mean. Searching for the best parameters in a mathematical formula that minimize the error of your prediction. In the model you have to find the best weight. Okay, for example, for each input you have the weighted one, W1, W2, W2. What I said, in the model you have to find the best weight. Randomly the weights coming, later on you can find the best weight. So in figure 4, usually the weights are randomly initialized. Okay, randomly. You can tell me why the weights is 1. This is randomly, or by random code, the weights can be initialized and adjusted. Then adjusted as a learning process. Later on they will adjust. Here I will just set them all as a 1. At the beginning you can put all weights, for example weight 1, weight 2, weight 3, 1, 1, 1. Then it's time to multiplication. Why multiplication? Because we have the formula W1 x1. So here we have the multiplication. This one, and this one. So it's time to sum over sigma. We have sum of them. When you calculate in figure 5, so far we haven't done anything different from the linear regression. Here it means that it is a linear regression. So it's time to do something novel. So in previous one I told you we haven't done anything different from the linear regression, which is pretty straightforward for the business to understand. Now here is the upgrade from the linear model. In figure 5, upgrade from linear model. For example, we have the sigma xi multiplied by wi equal to y to a non-linear model. Okay, upgrade from linear model to non-linear. What is the non-linear one? If sigma xi multiply wi equal to y. Then enter the activation function. So it means that this one is already done and you have to do one activation function to reach this target value prediction. For activation function we have different type of them. For example, sigmoid, tangent, ReLU, and binary step that you can see in this picture. We use the NumPy package to implement and show them the total aspect of neural network will be used in our Python code. I shall use a binary step activation function that return 1 or 0 only. Okay, 1 or 0. In figure you have it. So also we have different type of activation function that I told you: sigmoid function, tangent, ReLU, and binary. We have the output of our perceptron, a single neural network that takes some input and return one output. Now, the training of the model would continue by comparing the output with the target, calculating the error, and optimizing the weights, reiterating the whole process again and again. This is the procedure that we have to focus on it. As I mentioned to you, we have different type of activation function. Let's try to show you sigmoid, tangent, ReLU, and binary activation function. This is the different activation function which I try to plot it. This different activation function we already discussed before, and I suggest you look at the main book of neural network and understand what we have in this activation function. For example, here we have one example. We shall use a binary step activation function that return 1 or 0 only. Okay, here we have input, this one, multiplied by weight. I told you the weight, I randomly selected 1. After you get this value, you sum all of them, sigma xi multiplied by wi. After this, you put the activation function. The activation function can be selected based on one of your favorite activation, for example, binary step or tangent, sigmoid, ReLU. If, for example, x greater than 0, fx equal to 1. If x greater than 0 or less than 0, fx equal to 0, and so on. So now you see here we put one activation function like this formula. Okay, this is look like the binary step. If x greater than 0, fx will return 1. If x less than 0, fx will return 0. So now what is your x? After you find it, for example, here is 0.6. Then put it here. F or function of 0.6. Which section is it? Because 0.6 greater than 0, fx will return 1. That is why your target is predicted as 1. Here is the inside the neurons. This is very beautiful interactive picture. The input came and the input multiplied by weights, you see here, then fx will be happen, then fx equal to y hat, then it's returned to 1, means that our target are predicted as 1. This is very simple way that you understand how by one single neural network or single layer neural network, how it takes some input and return one output. The single neural network or inside the neural or neurons shown here. Now it's time to discuss about network topology. A network topology is the arrangement of a network along with its nodes and connecting lines. According to the topology, ANN can be classified as the following kinds. Okay, ANN can be classified as the following kind of neural network. One is feed-forward networks, one is feedback networks. So let's talk about feed-forward networks. What is it? We have single layer feed-forward network, we have multi-layer feed-forward network. If you look at to the original picture of neural network or ANN, we have one hidden layer, okay, one hidden layer, and we have one input, one output. One input means one input layer. In layer there are many inputs. Be careful. When I said one input layer, it's not like one input neurons or nodes. One input, you can put many variable. So let's have a look to this single layer feed-forward networks, multi-layer feed-forward networks. Here is multi-layer feed-forward networks. For feed-forward networks, it is a non-recurrent network having processing unit or node in layer, and all the nodes in a layer are connected with the nodes of the previous layer. The connection has different weights upon them. There is no feedback loop, means the signal can only flow in one direction, from input to output. Also, it may be divided in the following types. The following types I already show you. We have the single layer feed-forward. The concept is of feed-forward ANN, means that having only one weighted layer. In other words, we can say the input layer is fully connected to the output layer. You see, full connected, each node connected to each other. So in the right side we have feed-forward network, but multi-layer feed-forward network. The concept is of feed-forward ANN having more than one weighted layer. Here weighted layer, here also weighted layer. More than one weighted layer. As this network has one or more layer between the input and the output layer is called hidden layer. Here in single layer we don't have the hidden layer, but in multi-layer feed-forward we have at least one hidden layer. Be careful of this one. What is feedback networks? As the name suggests, a feedback network has feedback paths. You see, one pass, another feedback, which means the signal can flow in both directions using loops. This makes it a non-linear dynamic system. For example, in this picture, you can see a fully recurrent network. It is the simplest neural network architecture because all nodes are connected to all other nodes, and each node works as both input and output. This is the feedback networks. So let's have a look how many layers we have. The right answer is try different variant and see what works. No hidden layer, some hidden layer, too many hidden layer. Now it's time to discuss about backpropagation neural networks. The backpropagation neural networks, or BPN, is a multi-layer neural network consisting of the input layer, at least one hidden layer, and output layer. As its name suggests, backpropagation or backpropagating will take place in this network. the error which is calculated at the output layer by comparing the target output and the actual output will be propagated back toward the input. You can look at this procedure in this figure, back propagation neural network. They go forward and backward. I already explained to you for the training of back propagation neural network, we'll have the following three phases. Phase 1, feed forward phase. Phase 2, back propagation of error. Phase 3, updating of weights. So, as it is clear from the diagram, the working of BPN is in two phases. One phase sends the signal from the input layer to the output layer, and the other phase back propagate the error from the output layer to input layer. This is the whole procedure of BPN. Now it's time to implement ANN in Python. For implementation ANN network, we will explain two packages, scikit-learn and TensorFlow. First, we classify iris dataset using scikit-learn. Then we will explain MNIST classification using TensorFlow. So IRIS classification using scikit-learn package. So we use the classifier provided by scikit-learn module of Python. In this code, we will use the multi-layer perceptron classifier, MLP classifier, contained in scikit-learn.neural network. You see here, import module, we loaded dataset, iris dataset, and like the previous one from the model selection, we have the training test split, we have a standardization, and here is new MLP classifier. Okay, accuracy, confusion matrix, and classification report also provided for you before. So now it's time to run this code, and next time is to load the data and splitting it into training and test dataset. We will use again this RIS dataset, which we had used already multiple times in our machine learning course in Python. For more details, go back and see what is a RIS dataset. Now it's time to read this dataset, load the dataset, and print it the sample and feature. Let's have a look. Yes, we have 150 sample and 4 feature. Okay, and sample and 4 feature that we have it. So next step is to split the data into training and test dataset. Here we got 20% test and 80% training. So like the previous one, dataset here, after you run, is already done. Now it's time to scaling the data. I told you before, the scaling the data. So we feed the train data, then we scale the training data to training and testing, then we print it. So how can we see that? This one is the data set that we already have it. So this is the fitting the data. The next step is to train the model. First, you have to create a classifier from the model. I told you MLP classifier. You can mention the hidden layer size, for example 10.5, and maximum iteration that in training they have to do. Let's fit the training data to our model. Okay, training data to our model and training label also you have. After you run it, you can see MLP successfully, the classifier model already done. Now it's time to evaluate the model by using predict mlp.predict for the training part and mlp.predict for testing part. In most paper and publication, the examiner will look at your test section. After you run it, you see that in training it is 98% and in testing is 93%. Of course, it's correct because in testing something will be happen because the data unknown gave to the system. Now it's time to use the confusion matrix for training data. Here is confusion matrix, true positive, true negative, whatever you have, and confusion matrix for test data. And F-score also is available here. So here is the report for the classification that make a more interesting part for you. Here, the report that I want to see from your task. For example, we have 3 classes. For example, we have precision, recall, F-score, and support. So this one is whatever we achieve. So most part are F1 score, which is 93% in terms of the testing part. So the rest should be read with more details. So now it's time to give another example, means classification. So what is this data set? We call the means data set of handwriting digits. So here, this data set, MNIST data set of handwriting digit available from the page, this page, has a training set of 60,000 example and a test set of 10,000 example. It is a subset of larger set available from NIST. The digital or digit has been size normalized and centered in a fixed size images. It is a good database for people who want to try learning techniques and pattern recognition methods on a real world data while spending minimal effort on a pre-processing and formatting because this is already formatted. So the file already available here, and you can find this database from other sources, and here they apply many things on it. We don't want to focus. I just wanted to show you what is this dataset about. And it's time to import the module. We want to use the TensorFlow. The TensorFlow already imported, and I hope we already installed it. If no, I can return and show you how to install this TensorFlow. Now it's time to explain the TensorFlow package classification of dataset that I mentioned to you using the TensorFlow. You have to import the TensorFlow and you have to import the dataset from the TensorFlow.cross model. You have to import sequential, dense, and to categorical. Let's run this step, and we are waiting. And now it's time to load the dataset, which I mentioned to you. The dataset already loaded. Now let's shape the training. The training phase, they have 60,000 records. And for the test also, they have this shape of 10,000, and now it's time to reshape. We call configuration option. So we have the configuration option, reshape the data. I already reshape the data by this option. So MLP do not understand such thing as a 2-dimension. That is why you have to reshape to 28 multiplied 28 pixels, which is 784 features that we have. Then let's have a look to xtest.shape, okay, and ytest.shape. That is why we converted it. So it's time to convert into grayscale. So it's time to put the grayscale because this is the images. So after you put the convert to the grayscale, now it's time to convert to the target classes to categorical ones. So we already did. It's time to create a model. All the previous step we call pre-processing. In order to create a model, first you have to set the input shape. I put the input shape, depends on the feature vector length. I can print it out, and then after this I create the model. I told you we have sequential, dense, and here also dense. The activation function I already introduced, ReLU, and for the dense, which is the end of system, we have the activation function softmax. Let's have a look to model summary that we already did it. Here is the model summary. The model is sequential. The layer, in the layer of neural network, we have dense 1, dense 2, and output shape and parameter that we have. It total parameter is 292,000, and trainable parameters is this one, and non-trainable parameter is 0. Now it's time to do the training. Let's do the training, and we put epoch. How many epochs? Maybe more than 9. Is it 10 epochs which the system calculated for us, and we use the model fit for our system. Now it's time to use the test model. For the test model, you can see the accuracy after this test model will reach to 97%, and which is good, quite good. So I hope you understand the total description of ANN.